Welcome to my first video of calculus lessons. Since I didn't start the videos at the beginning of the year, you'll notice that I'll be starting at continuity. So let's go and begin. So a continuous function, you have been preached and burned down by the simple definition of a continuous function, and they've always told you that a continuous function is a curve that you can draw without ever lifting up your pencil or having to stop or anything like that. As you notice, the curve that I drew, the curve is continuous. There's no holes, there's no gaps, there's no asymptotes, therefore a continuous function at every point. Well, in calculus, they have a specific definition of continuity, and it goes as follows. A function f is said to be continuous at x equals c if and only if the first condition says f of c is defined. What does that mean? Well, it means that if I were to go on the graph and choose any x value for c, and I were to go down or up depending on what you chose, does the point exist? And yes, it does. There does not have to be a solid dot in order for it to be an existing point. Simply the curve would tell you that it's existing. Okay, that's the first condition. The second condition says the limit as x approaches c of f of x exists. So what this says is that if I choose that same c and I approach it from the left and I approach it from the right, do they approach the same point? And the answer is yes. Okay, so the first condition says the point has to exist. The second condition says the limit must exist regardless whether the point is there or not. Okay, so we haven't really fully analyzed the definition yet. Now here's the most important part of the definition. The third condition is the limit as x approaches c of f of x must equal to the f of c, the point. In other words, the limit equals the point. And as we can tell from the picture above, the limit exists, the point exists, and they both seem to have the same y value. In other words, if I were to trace this point right here, I can see that the limit, and the point equals the same value. So that is the definition of a continuous function. And you can test this function at any c you want to test it on. It doesn't have to just be that one point. Okay? So to better understand this, we're going to go ahead and see some counter examples of continuous functions. So letter A says sketch a function f so that f of c is not defined. And if you pay attention very closely, this looks a lot like the first condition. It looks like the counter example of the first condition of continuity. So we're going to go ahead and draw this continuous function to better understand what it means for a function to be continuous. So this simply says draw a graph with an open hole somewhere in the graph. And if that is my c value, my f of c does not exist because it's not there. So that is a discontinuous function. Letter B says draw a graph where the limit does not exist. Okay, so there are many variations of how you can draw these examples. I'm just choosing one. So I'm going to draw the same curve just to keep this pretty simple. Oops, no. I'm not going to draw the same curve because if I drew that same curve, the limit existed and we don't want it to exist. So I'm going to draw another curve up here. And it looks like from the limit from the left, the limit from the right are two different y values. So the limit does not exist, which fails condition number 2 if you pay attention to the definition above. The letter C says, now draw a graph where the point exists and the limit exists, but the point and the limit are not the same. Okay, so same curve, something like that, except I'm going to have an open dot here. So disregard that little filled in part. So there's an open dot here, and I'm going to draw a dot up here. Okay, so this dot tells me that f of c exists, which is the first condition of continuity. And because the limits seem to be approaching the same number, the limit exists. Now, f of c does not equal the limit, which is the third condition. This fails the third condition of continuity. So there are your three examples of discontinuous function. Now let's draw an example of a continuous function. There are many variations. So I can choose this to be my c, and I notice that the point exists, the limit exists, and the point and the limit are the same value. Therefore, continuous at that point. And they're actually continuous at every point in this graph. Now I want to talk about three types of discontinuities. The first type is called a point discontinuity. Pretty much is an example A all over again. In other words, the graph exists except for a single point, which is right here. That is a point discontinuity. Number two is a jump discontinuity, which is an example B. So I'm going to put here example A. This is example B. I don't necessarily have to have two open dots. I could have one open and one closed. I cannot have two closed because then it wouldn't be a function if you do vertical line test. So there's an example of a jump discontinuity. In other words, if I approach the limit from the left, I get this number, this number. If I approach the limit from the right, I get another number, and those numbers are not the same. So the graph jumps. Now, the last one, which we haven't discussed, is called an asymptotic discontinuity. So I'm going to say this is my C, and I'm going to draw an asymptote right here. And I notice that if I draw a curve like this, obviously you guys already know the limit does not exist because they don't meet. The point does not exist because the asymptote tells you there's no point at that x value. So this fails condition number one, this fails condition number two, and obviously if you don't have one or two, you cannot have condition number three. So that is your discontinuity. Those are your three types: point, jump, and asymptotic. Now, to go back to point discontinuity, there are two types of point discontinuities. There is a non-removable discontinuity, and there is a removable. Number one is an example of a non-removable. I'm going to abbreviate, non-removable. To make number one a removable, simply plug in a dot somewhere above or below the open dot, and now you have a removable discontinuity. To put it simple, a removable discontinuity is when you have a graph that has an open hole, but you plug it in somewhere else above it or below it. Okay? A non-removable discontinuity would mean that there is no other point to plug in that dot. Now the example below, we have a square root function. Okay, so it says here a function f is continuous at a left endpoint, okay, if the limit as x approaches a from the left is equal to f of a, and the limit as x approaches b from the right is equal to f of b. Okay, so that looks very confusing, especially if this is your first time watching the video and your first time being exposed to all these symbologies and calculus terminology and things like that. So if you graph this function, it's a semicircle. For those of you that remember your conics, you know that that's a semicircle with radius 5. So here's 5, here's negative 5. And the example says this function is continuous on the closed interval from negative 5 to 5. Okay, I'm pretty much doing the bootlegging right now. If you get a calculator out, you'll see that you know what I'm talking about. So the function is continuous at every point inside this circle. Now this definition up here says that endpoints are also considered continuous only if the limit from the left of this endpoint exists, which is 0, and the limit from the right of this endpoint exists, which is also 0. Okay? And it equals to a point. If it was an open dot like this, then there would be a discontinuous point at that x value. So you can verify this, get a graphing calculator, put it on there, and you'll see that the function is continuous. You can trace it from left to right, and there are no undefined points. So I'm going to go ahead and split off to the next video. So I'm stopping here, and I'll watch you at the second video.